These are the notes on functional groups. You should have already completed the straight chain hydrocarbon notes before this. It'll be helpful to have the formula sheet available as you go through these notes. So what's the purpose of functional groups? Functional groups are often highly reactive. They change the properties of a molecule and are commonly found in biological systems, pharmaceuticals, nature, fuel, plastics, and more. Double and triple bonds can be considered functional groups as well as the four we're going to discuss in this class. And we talked about about the double bonds, that those are our alkenes. And then our triple bonds, those are alkynes. And so we talked about those in our first set of notes on those straight chain hydrocarbons. And those change properties because we don't have the hydrogens that are surrounding the carbons that might have a double bond with that ene ending or a triple bond with that ine ending. So functional groups are special attachments to the longest chain or the parent chain. There are branched hydrocarbons where we might have a straight chain and then there are carbons that are branching off in the middle. We did not cover those, and so when we're looking at these, they are going to be our straight chain of hydrocarbons that might have a special group and attachment on something. All of the examples are alkanes, those single bonded parent chains. Again, because being an alkene or an alkyne is already going to change the properties of that molecule. And so we see these alkanes with these other groups on them because that's just where they most commonly occur. So when we're looking at naming, we keep our alkane name. We are going to drop the E at the end, and then we add a new ending. And then that ending is telling us that functional group or that special attachment that is in our molecule. So an example, propane, and remember prop, we have that prefix on our formula sheet as well. So prop, that means 3 carbons, and those are single bonded with the alkane. So it's all just a single chain. So if we were looking at like propanoic acid or propanol or propanal, that ending is what is going to change. But we still are looking at what is our chain and how long is the chain. That part is still going to be in our name. And our condensed formula can indicate the structure of our molecule, where that functional group is located. We're going to look at how can we, and then our molecular formula just tells our total numbers of those atoms, not where specifically in that molecule that functional group is. We are going to discuss 4 functional groups. These are on your pink sheet as well, some information about them, so you do not have to be memorizing them, but we're going to look at how we would see it in the formula, where those functional groups can be, and what some of them might look like in the first part of these notes. So our first functional group is the hydroxyl group or the alcohols. So anytime we've heard of an alcohol, that is talking about a hydrocarbon that has this special group on the end. And the formula of an alcohol is that it is an OH group anywhere in our molecule. So we need to use a number in order to indicate where in that molecule that OH group is. We would change the suffix, the ending of our word, of our name to OL, and that indicates that OH grouping. So uses, we see beverages and fuel are alcohols, hand sanitizer. It's probably something you are used to hearing, you just might not know what that means. So let's look at this alcohol here. We can see it's an alcohol because there's this OH group off of one of our carbons. And notice that this takes the place of just a hydrogen. We need that oxygen though. Oxygen's happy with 8, but it has 6, so it needs to bond to the carbon. And then it is also bonding with a hydrogen to get oxygen to that full octet. And why is this going to lead to special properties? Well, remember our oxygen is more electronegative. And so it does create a nonpolar molecule when we have a hydroxyl group. So the name of this, we are going to look at our chain. So I have a chain of 2 carbons. If we go and look at our prefixes, 2 carbons is going to be that prefix eth. These are connected just with a single bond. So that is ethane. But when we're looking at these, we are getting rid of that E ending. So getting rid of the E, and we are putting that OL on the end to show that that is ethanol. That OL tells us we have an OH group. And it says here we should use a number. If we look at our numbering, we always number for our group to be at the, or our anything special to be at the lowest possible spot. So this would be 1 and 2. And so it's on that first carbon. Well, I don't have any other place for that to go. And so this one actually doesn't need a number because we have those kind of less than, because we don't have 3 carbons to indicate that it's in the middle with that. And so this one we don't need a number because it needs to be on the end. And so no number needed just because we have only 2 carbons. If we were to go through and actually writing out that other compound, we would start with this carbon. We could actually start on either end, but with the condensed formula, we would say CH3. That represents this grouping right here. And then we would say CH2, and then we would put our functional group of OH. So we are going to keep this OH group. We're going to keep it because that carbon is connected to 2 hydrogens and that oxygen, but the oxygen is what's connected to that last hydrogen there. So we do see our OH in that formula. We would, even if we were kind of doing the molecular formula, we might see C2H5 for these 5 hydrogens that surround our carbons. But then we would put the OH to indicate that it is an alcohol. All right, looking at our next one, we need to figure out how long our chain is. We have 5 carbons. The prefix for 5 is pent. They are all connected with a single bond, so that's pentane. But I see an OH group, and so I get rid of my E, and I am going to put an OL, so pentanol. I need to say, though, where is that? It could be anywhere. And so I need to do my numbering so that it is at the lowest spot. 1, 2. This is going to be 2 pentanol, because 1, 2, 3, 4, 5. We wouldn't number 1, 2, 3, 4 because 2 is less than 4. So this would be 2 pentanol. If we were looking at writing out those compounds, we can say my molecular formula, I would say C5, and then I would say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, H11, and then that OH would be on there. Separating this hydrogen, that we always see that OH grouping, even if we are doing a molecular formula. The condensed formula that again shows the structure of our atom is going to be CH3, and then we would have CH for this one here, and then I would have that OH, and then I have my CH2, CH2, CH3. You could always group those together if you want in parentheses and say you have 2 of that grouping. How would this look on a line structure? Well, our line structure, we're going to show those 5 carbons, 1, 2, 3, 4, 5. Remember, each endpoint represents a carbon. So 1, 2, 3, 4, 5. Well, on my second carbon, I have an OH. And so we actually show that one bonded, and then we show that OH grouping off of there to indicate that's where it is. All right, so that is our hydroxyl or alcohol functional group. And again, it creates a dipole, and that's going to that is going to attract things that have partial positive charges. Our next functional group is an aldehyde, and that is going to have a carbon double bonded with an oxygen on the end of a molecule. And so with this one, we don't need a number because it's only ever at the end. We know it's going to be on one of those ends. It doesn't matter which one. We could draw it either way. And then this is going to have an Al suffix. So aldehydes, you've probably heard of formaldehyde before. Aldehydes are used in preservatives. So if we look at this one, we still use that strongest chain. I can see that functional group that there is a carbon double bonded with an oxygen, carbon double bonded with an oxygen here. Notice both of those are on the end because that is part of being an aldehyde. And so we look at, well, what is our longest chain? This one has a chain of 2. So 2, the prefix is F. These carbons are double bond or are just single bonded. So then this would be ethane, but we get rid of that E and we're going to add the Al on the end. So ethanol. Looking at our next one, we've got a chain of 1, 2, 3, 4, 5. So 5 is pent. These are connected with only single bonds, so pentane. We get rid of that E and then putting on that Al ending to show that this is an aldehyde. If we were to go ahead and draw this, I will draw the line structure for pentanal. We've got 1, 2, 3, 4, 5. And then we would have an oxygen. So here's my 5th carbon. 1, 2, 3, 4, 5. So on the end point, and it could be on either end, I'm going to just draw it on this end because that's how this structure was. It would be the same name if that oxygen was double bonded on the other side. We're going to show a double bond with that oxygen off of that carbon. So the only thing we're ever writing is something that is a non-carbon or a non-hydrogen attached to one of those carbons. If I wanted to go ahead and write out my condensed formula, I could write CH3, that's for that first carbon, CH2, 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 and I would have CHO. That shows this carbon, the one hydrogen on it, and then that double bonded oxygen. And we could also take this and say CH3. We have CH2 1, 2, 3 times, and then that CHO as well. So either of these two would be good for your condensed formula. All right, our next functional group is ketones. These are also an oxygen double bonded to a carbon, but it is in the middle or on an interior carbon. So we do need to use a number to indicate where in that chain our functional group is. With ketones, we are going to change the ending to an ONE ending. So perfumes and paints are things where we will see these ketone functional groups. Again, it's because that carbon oxygen, the oxygen's more electronegative, creating that dipole that's going to attract things with positive charges. Looking at this first one, I gave us the skeleton structure of that. As we are looking at it, I am going to go ahead and name this. Well, let's look at that chain, 1, 2, 3, 4, 5, 6, 7, 8. So that is a chain of 8, which would be, which is oct. And then we have octane would be if that is just a chain of 8. But with this one, we have that oxygen double bonded on a carbon. So we need to get rid of the E ending, and we are going to change that to an ONE. So octanone, which sounds a little funny. And then we do need to say, though, where could this be? Because as we look at it, it's not going to be on the first carbon, but it could be on the second, third, or fourth. We could also number it this way, 1, 2, 3, 4. So we could have 2-octanone, 3-octanone, or 4-octanone. We would never have a 5-octanone because we would number the opposite way so that our numbering was as small as possible. But we have these options, 3 different places that functional group could be. So we do need to say that this is 2-octanone to indicate it's on our second of our carbons with that. We could go ahead and draw this out with each of these being those carbons. It would look similar to this, but we would have a chain of 8 with that functional group on the second of the carbons in that chain. If we wanted to write out the condensed formula for that, we have, here's a carbon, and actually I'm not going to do that right now because we would need to kind of see that. We'll write out the condensed formula on this one. Looking at this next one, I'm looking at that chain. I have a chain of 1, 2, 3, 4, 5, 6. So we've got 6, which is hex. They're connected in a single bond, so that would be hexane. But I have a functional group, that carbon-oxygen double bonded, just like we see here. And so we are going to indicate that by getting rid of the E on the end here and changing that to an ONE to show that we have a ketone functional group. So this is hexanone, and where is it at? Well, we need to look at our numbering. 1, 2, 3. This is 3-hexanone. If we were to number this way, 1, 2, 3, 4. 3 is smaller than 4, and so we're going to want a number from the left. So that is 3-hexanone. If I wanted to write out my condensed formula, I can do that with my first carbon, and I have 3 hydrogens on it, so CH3. My next carbon, I have CH2. Then I have that CO functional group. Then I have CH2. I have another CH2 and CH3 as the end there. So that would be the condensed formula. If we wanted to do the skeleton or the line structure like we did here, we would do that chain of 6, 1, 2, 3, 4, 5, 6. And then I'm going to show that oxygen double bonded 1, 2, 3 on my third carbon, just showing that with the double bond and showing the oxygen on there. We do need to indicate any elements other than carbons and hydrogens on those skeleton structures. All right, the fourth functional group we are going to look at or discuss are carboxylic acids. And this would be on a carbon, a terminal at the end of the molecule, an end carbon. We would have carbon with an oxygen, and a hydrogen. And so we can see this here, that carbon is going to have 1 double bonded oxygen. That's this one. And then 1 oxygen with a hydrogen as well. And these have to be at the end because carbon has to be able to have 1, 2, 3 things that it's bonding with aside from another carbon. That wouldn't be possible if it was in the middle. And our suffixes on these are oic acids. So things like vinegar is an example of a carboxylic acid. So if we look at this one, we again look at what is our chain. My chain here, I only have 2 carbons. And so 2 is eth, and then they're single bonded, so that would be ethane. We get rid of the E ending, and we say oic, ethanoic acid is the name of this. We don't need a number because it's always at the end, whether it's at the first end or the second end. So this is ethanoic acid. And as we're looking at this, if I want to write out my formula, CH3, I have that there. And we do normally put that COOH at the end instead of at the beginning. So we usually put it at like the end of our formula as well if we are looking at our writing out our condensed formula. What would this look like as a line structure? Well, I would have my 2 carbons here. There's my 2 carbons, 1, 2. And then we would have an oxygen that's double bonded. And then we would have an oxygen that's single bonded with that H. So you could do that just a line with the OH, or you could also do OH. We most commonly would show that as just that OH right there, showing that kind of branch off of that carbon. All right, so those are our 4 functional groups. As a reminder, you don't need to memorize these. This chart, which talks about the alcohol or hydroxyl functional group, aldehydes, ketones, and carboxylic acids, it has the formula of each, the location, and the name endings on there. And so you have this and the prefixes on your pink sheet to use as you are looking at these. All right, let's go ahead and do some examples and practice recognizing functional groups and looking at the representations of those. So we are given that displayed formula, that Lewis structure. Depending on where you want to start, we can always just translate that into a skeleton or line structure. I see I have 3 carbons, and so I can show that with 1, 2, 3 endpoints. And then it looks like I have a oxygen double bonded on that last carbon. So I'm going to show that just with a double bond off of there, showing that oxygen, something other than a carbon or an oxygen. A carbon or a hydrogen. We need to write what that element is in our line structure. So looking at this, and we could write our condensed formula and our molecular formula without needing to recognize the functional group. My condensed formula is going to just list each carbon and what is on it at a time. And so that first one we have CH3, that's for this one. Then I have CH2, and then I have CH, and then that O on there. My molecular formula is really like is a tally of those parts. So I have 3 carbons, C3. Then I would do my hydrogens. I have 1, 2, 3, 4, 5, 6 hydrogens. And then we would have that O. But what is this actually? I have a carbon double bonded with an oxygen. If we look back up here, we have 2 where we have those carbons double bonded with oxygens, aldehydes and ketones. But terminal means on the end. The middle, an interior carbon, we would need to use the number. This one is an aldehyde because that oxygen is double bonded on an end carbon with that. And so this is an aldehyde, meaning we're going to need to use that ending of Al to show that. So our functional group is an aldehyde. You have that chart that I just had on the screen. And so you will be able to use that. And so we need to then first look at, well, we have a chain of 3. For 3, that is prop. These are all carbons that are single bonded. So that would be propane, but with that functional group, we are going to actually add that ending as Al. So this one is propanal. Looking at our next one. So looking at that, we can start wherever we want. Let's start with maybe our functional group and our name this time. So I have that chain of carbons, and I can see what is different. I have a oxygen carbon double bond here. So as we look up here, those oxygen carbon double bonds, I've got that in the middle now, which means that this is a ketone instead of an aldehyde. So the fact that that's in the middle makes this a ketone, and we are going to go back to that example and we can fill that in. So that ketone, as we look at naming, we look at what is our longest chain. We have a chain of 4. That prefix for 4 is bute. It's a chain of carbon single bonded, which would be butane. But for a ketone, we change that ending to ONE, butanone. And we would normally need to say where this would be. We would need to use a number, except for we know that this needs to be on an inner carbon. Anyway, we look at this, 1, 2, or if we were to number this, 1, 2, 2 butanone, that would always have to be on the second carbon. If it was on this one, we would number from the left. It would be 1, 2 if that's where that double bonded oxygen was, but it is here 1, 2. And so for this one, we don't actually need the number just because there is only 4 in the chain. If there were 5, we would end up needing a number. All right, if we go through and write the condensed formula, our condensed formula is going to list, I've got C and then 1, 2, 3, 3 hydrogens, that's for that first one, CH2, I've got CO, and then CH3. We could also write this one and put that CO second. That would also be fine as well for those. Writing our molecular formula, that is just going to be the molecule. What is the tally of parts, everything we have? We have 4 carbons. I have 1, 2, 3, 4, 5, 6, 7, 8 hydrogens. And then I list my oxygen last. Drawing my skeleton or line structure, I'm going to start with drawing my chain. 1, 2, 3, 4. Each endpoint represents a carbon. And then on that second carbon, so I could put it here if I want, or if I just mirror this and have our numbering going from the right, 1, 2, I can put that double bonded oxygen off of that point. So those 2 lines show it's a double bond, and then we are going to write that oxygen symbol there. All right, let's look at example 3. As we're looking at this, we have a chain of 2 carbons. What is different than those hydrogens? Well, this one has a double bonded oxygen and an OH. A double bonded oxygen is a ketone or an aldehyde. An OH is an alcohol, but when we put those together, that is our carboxylic acid. So we see this here. And so this is a carboxylic acid functional group. We write the chain. It's a chain of 2. Eth is a 2. Ane, because these are single bonded. And then when we are getting rid of that E on the end, now our ending, because for those carboxylic acids, we add on oic acid. So this is ethanoic acid. And carboxylic acids, these are always on the end, because if it was not on the end, the carbon wouldn't be able to fit both that oxygen double bonded and the oxygen hydrogen group. So we do not need a number because these are always on the end. Our condensed formula, we start with usually the end that's opposite of our functional group, but we could start on this end if we want. But we usually list all of our just carbon hydrogens, and then these go at the end. So this one is going to have a CH3, and then we list COOH with that carboxylic acid. So the carbon, then the oxygen, and then the carbon-oxygen hydrogen group. Molecular formula for this one, we have 2 carbons, we have 4 hydrogens, and 2 oxygens. That molecular formula doesn't tell us any information about the structure, and so that is why we have those condensed formulas. Those really help us see what's going on. Doing our skeleton or our line structure, here's my line that represents my 2 carbon. We'd usually do those at angles because we do those as a zigzag. And then this is going to have an oxygen double bonded and an OH. So it kind of looks like that branch. We've got the double bond here and then that branch of the OH off that second carbon. Example 4. This one we're given is 1-butanol, OL ending. That tells me that this is an alcohol functional group. And alcohols can be on any carbon. This one is telling us where it is. And so this is going to be on the first carbon, bute being a chain of 4. So I'm going to draw my chain of 4. 1, 2, 3, 4. And that is going to be an alcohol group. An alcohol is an oxygen hydrogen coming off of 1, the first carbon. And you can just do this with a line with an OH. You could also, if you want, do this with an oxygen and then a hydrogen off of it. Either of those are fine. You can just do that OH. And then we need to make everyone individually happy. So this carbon has that 1, 2 bonds. So then this is going to be 3, 4, and like that. So making sure each carbon has 4 bonds on it. This is butanol. These were all connected just with a single bond. And then as we look at this, we're going to have, we can write out our condensed formula now and our line structure. I'm going to do my line structure to show I've got 1, 2, 3, 4, and then I can show that is a single OH, showing that that is branching off of that first of our carbons. Doing my condensed formula. The condensed formulas usually will put the functional group at the end. So I'm going to start from this end, even though we're numbering this as number 1. You could do the CH2OH first, but normally the functional group, they like to put it at the end if they can, just because then you can kind of see what is changing the behavior of that molecule. So CH3, and then I have CH2, CH2, CH, OH. Oops, that is a CH2OH. So we can see that alcohol at the end of that group. This H doesn't get paired with these H's because that last H there is actually bonded with the oxygen. It's not bonded with this carbon. And our molecular formula would just be the totals. So we have 4 carbons. I can count up that I have 9 hydrogens and that 1 oxygen. Or even better, it would be that C4H8, and then you would show the OH as, so you can actually see that functional group, because otherwise we don't know what that functional group looks like. So this is a more common way to write that molecular formula. Example 5, we have this condensed formula, so C3COH, and I think I actually was supposed to do, let's ignore that. This is CH3COH. There we go, that's better. As we look at this now, let's look at what that, let's draw that out. We've got that CH3, so C, there's 3 H's. So that's this first part right here. And then I'm going to have my next carbon attached, and that carbon is going to have an oxygen and a hydrogen with that. And so with this one, all right, looking at this one, we have our condensed formula. Let's take this and draw out our displayed formula or our Lewis structure. So we've got carbon, and then that has 3 hydrogens. So there's that first chunk, CH3. Now I'm going to attach my next carbon, and looking at how this is written, I have a CHO because that H is before the oxygen. That means there is going to be a hydrogen bonded on just the carbon, and then our oxygen needs to be here, but we can't just have that 1 bond because carbon then only has 1, 2, 3 bonds and it needs 4, but oxygen also only has 6 valence electrons. So anytime it is just a carbon oxygen, it is a double bond. So that's what that is going to look like, and there is that third chunk. As we look at this, our skeleton structure, well, we can see we have our chain of carbons. I have a chain of 2 carbons. And then what we need to show is that on the end, there is a double bonded oxygen. So we show that double bond off of one of those carbons and writing that it's an oxygen there. So I have a chain of 2, which is eth. And if it's just in a single bond, that's ethane. But as I look here, I have a carbon double bonded with an oxygen. So I need to consider, is it on an interior carbon or an end terminal carbon? And this is on a terminal carbon, which makes this an aldehyde functional group. So when we get rid of that E ending, this is going to be ethanal, because that aldehyde functional group is always on the end with that carbon double bonded with an oxygen. Our molecular formula is just going to be that I have 1, 2, so 2 carbons, H4 hydrogens, and 1 oxygen. And again, our molecular formula doesn't tell us information about the structure, which makes it harder to tell the functional group. All right, example 6, this is the last one we're going to do together. We're given that skeleton or that line structure. I've got 1, 2, 3 carbons, so I'm going to go ahead and just draw out that chain of carbons. And looking at what else there is, I have a oxygen double bonded. So let's draw that. And I'm just copying the structure that I see in my skeleton structure. You could always flip it or mirror it so that the functional group is over here if you wanted. And I also have that oxygen hydrogen, which is another part of that functional group. And I can either put that on the end here. I could also put it on the bottom. It doesn't matter. I'm going to do this with an OH. And let's look at if everyone is happy. This carbon only has 1 bond, so it needs 3 hydrogens. This carbon has 2 bonds, so it needs 2 more hydrogens. This carbon has a bond attaching it to its chain, so 1, 2, 3, 4, so that is happy. As we look at this now, I see that I have a double bonded oxygen and an OH. So when I see both of those, that is my carboxylic acid functional group. So I need to look at what is the length of the chain. Well, this is a chain of 3 carbons, which would be propane, but we get rid of the E, and carboxylic acids, we change that ending to oic acid. So this is propanoic acid. Writing our condensed formula, I'm going to just start from the left and work my way through, putting that functional group last, which is what we normally do. CH3, CH2, and then we do C, and I'm going to do the O and then the OH with that. So usually we do see that COOH, that double bonded oxygen goes first, and then the oxygen hydrogen group. We would not ever group these two in our condensed formula. And even though we name it with that functional, if propanoic acid, the functional group is always on the end. And even though when we number, we want the number to be as small as possible, putting the functional group on the end allows us to look at that to see, okay, is there something that's behaving not like just a regular carbon-hydrogen chain? Molecular formula is just combining all of those. We would have C3 for 3 carbons, H6, O2, but again, our molecular formula doesn't tell us what functional group we have. All right, so there are a couple more examples in these notes. I will post those, examples 7 through 10, filled out for you to look at on Schoology. There is also a worksheet for you to practice as well.